All right, what I'd like to do is go over a projectile motion problem. And so that problem is going to talk about, let's say, a scenario where we have a projectile that is launched from ground level, from, let's say, some sort of cannon, but let's just say that cannon is essentially at ground level, so I'll have to kind of put it below ground level, so that when the ball is launched, it is effectively at the ground. Now, once that thing is launched, let's firstly understand that the angle at which would allow it to go the farthest possible would be an angle of 45 degrees. Any other angle would be short of that. So let's say that we go to an angle of something like 60 degrees. That distance that it goes, known as the range, let's say that this right here is the range that it goes. That range would be the same, given that the velocity coming out of the cannon stays the same. That range can be the same at another angle as well. In this case, that would be 30 degrees. So 30 and 60 add up to make 90. They are reflections upon 45. They are each 15 degrees away from 45, and they would both hit the same spot. So where 45 hits a distance that is the greatest, as you go short of 45, or you change it from 45, you want it going short of that distance, given that you even keep the velocity of the projectile the same. So let's look at just how far the range actually is under some set of circumstances. So let's say that when something is launched, that it is going to be launched at an angle of, let's just say, 30 degrees, and we're going to draw a triangle to represent that initial motion. So this is going to be the initial velocity of the projectile, and let's give it a velocity of 25 meters per second. So it's shot at 25 meters per second at an angle of 30 degrees, and it is, of course, going to continue on and go, but this triangle just represents the initial motion. What we need to do is we need to break down the triangle into its parts, into its components of vertical. So this is going to be the initial velocity in the y direction, or the vertical direction, and this is going to be the initial velocity in the x direction. So let's look at SOHCAHTOA. I don't really need the TOA part at all for this, so I'll go ahead and get rid of that. The sine of the angle theta is equal to the opposite over the hypotenuse. If I were to find the opposite side of the triangle, and so in this case, this is the opposite side of the triangle, I'm going to multiply each side by h, and I will get that the sine of angle theta times the hypotenuse is equal to the opposite. Well, that means that here, relative to this triangle, the y component here, the y component, which is the opposite side, is going to be equal to the sine of, in this case, 30 degrees times the hypotenuse. And in that case, we're looking at 25 meters per second. And so we can plug this into our calculator and get some value. So if I go ahead and throw that in, we have the sine of 30 times the 25, that will give us 12.5, because the sine of 30 is 1/2. So that's going to be 12.5 meters per second. That means that this thing is going to have a vertical component of 12.5 meters per second at the initial launch. Keep in mind also that if you were to throw a ball upwards at 12.5 meters per second, it would come to the same peak height as this ball would in this scenario, and it would also be in the air for the same period of time as this ball would. Now let's look at the horizontal component. This same method, but using the cosine, you would come to the same conclusion, except you're using cosine. So this would be the cosine of angle theta times 25. And so the cosine of 30 degrees times 25 is going to give us 21.65 meters per second. And so I just rounded that off there for no particular reason. All right, so now that we have the components broken down, let me actually even circle those. So this is, again, the velocity in the x direction, and this is the initial velocity in the y direction. All right. Now, what we need to do is we need to figure out how long it's going to be in the air for. So the way that we can express this is we can say that we have this equation where v equals at. It's expressed in the Paul G. Hewitt textbook, the conceptual physics textbook. This equation works so long as the final velocity or the initial velocity is 0. And this here would be the other one of those two velocities. This must be the y component velocity, and this is going to be a y component acceleration. Those must be both in the same dimension of space. So, with that, we are going to rearrange this equation and solve for time. So, we have the y component velocity divided by the acceleration is equal to the time. Now remember that I said that this equation works so long as the initial velocity is 0 or the final velocity is 0. So the scenario in which we are looking at is this would be the time it takes for it to, again, remember that if I threw something directly upwards at 12.5 meters per second, it would be the same action. So if I were to throw something upwards at 12.5 meters per second, it would come to some peak height. In this case, the initial velocity in the y direction would be the 12.5 meters per second, but its final velocity would be equal to 0. So it would come to some peak height, and so this would represent the time it takes to max height. I'll just put an H for height. With that in mind, if whatever time it takes to get to the top, it's going to be twice as much time for it to come back down, because it also needs to make the return trip. So to solve for the total time, so I'm just going to write total t, this is going to be equal to, in fact, I'm going to say t is equal to 2 times the initial velocity in the y direction divided by the acceleration in the y direction. Well, the initial velocity in the y direction when we go back up is the 12.5 meters per second. So we're going to say that t is equal to 12.5 meters per second divided by, and that's, excuse me, it's going to be 2 times 12.5 meters per second, and that's divided by the 9.8 meters per second squared acceleration of gravity, or we could use 10 in either case. So let's see how long it would take for it to go. It would be 2 times 12.5 divided by 9.8, and that gives us a time of 2.55 seconds. So that is the total time that it will be in the air. Now that we have the total time in the air, the last thing that we need to do to figure out how far it's going to go, the range, we are going to then say that the velocity in the x direction is equal to the displacement in the x direction divided by the time it takes to get there. We can multiply each side by t, so that way the velocity times the time is equal to the distance in the x direction. This time is the same as this time here. It is the one variable that can flip-flop between the x and y direction. No other variables are able to do that because time is its own dimension. It is the 4th dimension. It doesn't have anything to do with the other 3 dimensions, other than the time it takes for it to go up and down is the same as the time it takes for it to go left and right. So with that, the velocity in the x direction is the 21.65. So 21.65 meters per second times the time of 2.55 seconds gives us the distance that it will go. And that will be a value of 55.23 meters is how far it will go. That will be its range in the x direction, right? So that's how we go about solving a projectile range problem here in our regular physics class with our conceptual book. And so here, and there's a little bit of the conceptual end to go along with it as well. Remember that the vertical component of velocity is affected by gravity, to where the horizontal component of velocity, yes, I did write that this was an initial velocity, but that never changes. The acceleration in the y direction is equal to 9.8 meters per second squared. But the acceleration in the x direction is equal to 0 meters per second squared. There is no acceleration in the x direction, to where there is acceleration in the y direction. That's why we have to break down these components in the way that we do. Because gravity affects only the vertical direction, it does not affect the horizontal direction at all. All right, hopefully that helps, and we'll have a good one.